Let's look at another example of the work energy theorem. The question reads, a skier of mass 70 kg is ready to ski. He starts from rest at point A and skis down an inclined slope of 30 degrees to the horizontal. He skis straight down from point A to point B over a distance of 120 meters without his ski poles touching the snow as shown in the diagram. The total kinetic frictional force between the skis and the slope was 150 newtons between point A and point B. So we want to determine the magnitude of the velocity of the skier at the bottom of the slope. Very interesting question. Now, we also have to stress this. You can do this question using other techniques of kinematics. However, we are interested in the work energy theorem. We want to solve that using the work energy theorem. So as usual, we look at this guy and we ask ourselves how many forces are acting on him. So since he's got a mass, it means he's got a weight. So he's experiencing a gravitational force which is always going downwards. Similarly, there's a surface, so there must be a reaction force which is the normal force. Bah, like that. Remember, it starts from rest. There is no push on him, so it means he's just sliding down the incline. There is no applied force. Now, as it slides down, this incline is rough, so you'll have a frictional force of 150 newtons acting on him like that. That is a very great free body diagram that we have. Now, just for interest, to be actually, which makes things easier, you just can look at this gravitational force to say, okay, it's not on the line of action, which means it's not on the axis in which the skier is moving. So let's take this gravitational force and resolve it into its components along the incline. So it's going to have a component here, which we're going to call FG parallel, because this component is parallel to the incline. It's also going to have another component there, which is perpendicular to the incline. We'll call it FG perpendicular like that. So the ones in black, it's the correct free body diagram. However, the ones in red is just us showing the gravitational force explicitly to show that it's got other the components on the line of action. So for us to determine the velocity and using the work energy theorem, we need to know that the work energy theorem states that the net work done on an object is equal to the object's change in kinetic energy, which means to compute the speed, we need the net work, or rather the net force before that. So let's do that. Now, since this object is moving down the slope, it means this is my direction of acceleration, and I'm going to take that as positive. Now, as it moves down the slope, this is my interest, this line. Now, this guy and that guy are perpendicular to the displacement of the object. So we already established that forces that are perpendicular to the displacement of the object have nothing, they don't do work on that particular object. So this guy and this guy, we can already cut them out because they're not doing work on the system. Now, remember, Fg, it's taken care of by the components. So my net force, F net, is going to be the gravitational, the component of gravity, which is parallel to the incline. It's positive because it's going down, Fg parallel, minus the frictional forces in the opposite direction. So we take the difference there. Fg parallel is the same as mg sine theta. Our theta being the angle there of the incline, minus the frictional force. The mass of this object is 70 kilograms. Gravitational acceleration is 9.8. Our theta is 30 degrees. Our frictional force is 150 newtons. Now we can type that in our calculators to see what is the net force acting on this particular object. So 70 times 9.8 times sine 70 times 9.8 times sine 30 degrees, which is 343. So you've got 343 minus 150, which is going to give you 193 newtons. This is the net force that is acting on this object as it goes from point A to point B. What does that mean? It means now, if we have the net force, we can say the work net is the same as F net times delta X. Our net force is 193 the displacement of the object from A to B is 120. So our net force is 193 and the displacement is 120. So 193 times 120 is 23,160 joules. This is the net work that is done on this particular object as it moves from A to B. Now, since we have the net work, we just go there and our work is simple. Work net is equals to change in EK. But let's expand the change in EK now. Half mvf squared minus half mvi squared. The net work is 23160 equals to half of 70, which is the mass of the object. The final velocity is what we're looking for, vf squared minus half of 70 times. Remember, we were told that this skier starts from rest, or he slides from rest. So his initial velocity is going to be a 0 squared there. Again, anything times 0 is dead, so this guy is dead. So we are left with 23160. Half of 70 is 35 vf squared. We divide by 35 on both sides. We divide by 35. What is 35 into that answer? 23160 divided by 35 is equal to 661.714 equals to vf squared. Now remember, at this point we're just looking for vf, so we're going to take the square root on both sides. So this simplifies to the following. You will have vf squared is equals to 661.714. You take the square root on both sides. Your final velocity is going to be the square root of 661.714, which is equals to 25.7 meters per second. So that's the final velocity, or the speed of the skier when he gets to point B, starting from rest at point A. Yeah, so that's how to compute it. Now let's look at how we could have done it differently. Remember, we said to find the net work, you could also opt to say the work net is going to be the work done by the force of gravity parallel to the incline plus the work done by frictional force, as opposed to the one we just did whereby you just found the net force. Now, if I want the work done by FG parallel, it's going to be my FG parallel times the displacement. Now, I don't have to put cos theta because I know that FG parallel is in the same direction as the displacement. So theta is 0 and then our cos of 0 is 1. Now, FG parallel is mg sine theta times our delta x. Now, the mass is 70, 9.8 sine of 30 degrees times 120, which is our displacement. Now, when we do that, we're going to put it in the calculator to see what it gives us. 70 times 9.8 times sine of 30, which is just a half, times 120 times 120. So we get the FG parallel to be 41,160 newtons. That's the work done by this particular force. Now, the work done by the frictional force is going to be the frictional force times delta x. Now, keep in mind that the frictional force is opposing the motion. So the angle between the displacement and the frictional force is 180. Cos of 180 is -1. Let's just put it, remember, but we spoke about it to say friction does negative work. So this is going to be cos of 180 degrees. The frictional force is 150 times 120, which is our displacement, times -1. So you get 150 times 120. You get a negative 18,000 joules. Excuse that. That's not newtons. We are not looking for the force. We are looking for the work. It's measured in joules. Excellent stuff. So now I've got the work done by FG parallel. I've got the work done by frictional force. I can sum them up to find the net work done on the object. So we can just hoy it in there. FG parallel, F1, 41,160 minus 18,000. How much is that going to produce? Let's see. So 41,160 160 minus 18, 160 minus 18,000. We get that our net work is going to be 23,160 joules, which is exactly the same work that we found previously. Now from this, you proceed using work net is equals to change in EK, and then you apply the very same technique that you applied. You should be able to find the very same velocity that we found, VF, I think it was 25 point something, and then you make like a mafia.